Let's now talk about part 2 of the reduced terminal operation discussion. This is going to talk about some interesting variants of collect and reduce, which are important to understand. And again, we'll use a good old Hamlet program as our case study to make these examples more concrete. We're also going to talk about the circumstances under which you can replace the use of reduce with sum. And this is actually useful because your programming assignments have been doing this in some of the cases, replacing the need for reduce with sum. You don't need to use reduce at all, and there are certain reasons why you might want to choose to do this. So far, we've used reduce to return a primitive value, right? So we took the names of the characters and the links of the characters in Hamlet. We turned it into a stream, we reduced it, and got a sum of the name links, which was a long. OK, great. However, you could also use collect to do this, if you so choose. So here what you can do is, instead of using reduce, you can say collect, and then you pass in a collector that takes each element in the stream as a long value, which is the capital L long, and then turns it into a lowercase long primitive. So summing long will do this summation on each element in the stream. It keeps basically a running count as the mutable state in the collector. So you could use collect there instead of using reduce. This also, of course, triggers the stream processing, just like reduce does. Reduce also triggers the intermediate processing. And that summing long is a collector that produces the sum of a long value function that's applied to the input elements. Likewise, reduce can be used to return a non-primitive value. Most of the time, it's used to return a primitive value, but you can also have it return non-primitive values. But you have to be a little careful here, as we'll talk about. And you can take a look at this example in my EX17 project in the Java 8 folder in my live lessons GitHub repository. So let's take a look and see how this works. So we're going to start out with all strings. I think I changed this. I think it should be all strings, maybe. I'll go back and look. So we create a stream of all the string objects in a list. And then what we're going to do is we're going to, got to figure out which one it is. We're then going to use the reduce operation, and we're going to start out by having the identity be the empty string. And then we're going to go ahead and concatenate everything together. So we're going to use the plus operation. The plus operator, when applied to two strings, creates a new string. And remember, strings are immutable. All strings are immutable. You can't have a non-immutable string in Java. You have to use something else, which we'll talk about later, like a string buffer or a string builder. So this is a way of being able to take all the words in the stream and make a single word string with them all concatenated together. Now, there's a problem with this approach, and the problem here is it's inefficient. And that's because there's a lot of overhead from concatenating all these strings, because every time we concatenate two immutable strings, we make a new immutable string, which is a lot of copying. And a very good observation has been made that one of the downsides with functional programming is you can create a lot of extra copies of stuff. So immutability has some virtues. It makes parallelization a lot easier. It, to some extent, makes reasoning a lot easier because you don't have to worry about side effects. But it can also make things really slow because you're doing a lot of extra copies and creations of objects. So you have to decide what's more important, performance or readability or semantical correctness or parallelization, whatever. Now, fortunately, there's a way out of this. And the way out of this is to use collect instead of reduce and use the joining collector. So there's a collector called joining, which will join together, basically concatenate all the elements in a stream, except unlike this approach, which uses concatenation of strings, joining uses mutable joining, so it'll make a local string builder, which is very fast, and it'll just tack each thing at the end of that string builder. So there's not a lot of extra copies. There's really no extra copies being made till you're all done with the final thing, and then you make a copy of that, perhaps. Now, another thing you can do, just to show you all the different variations, and this is actually quite important for your assignment, is you can also use reduce to return a stream. So this is a funky, weird corner case where we're using a terminal operation to return something that is itself a stream. right? Most of the time, terminal operations return non-stream results. Here's the exception that proves the rule for this, and you can see this in my EX35 example. And we'll look at that later. So here we are going to have something that's going to, we won't get into details of why we're doing this. We're doing it because we're using parallel streams. And we take the stream and we use map because we want this thing to run in parallel. And we end up with a stream of stuff. And we want to reduce it in, we have basically a stream of streams. And we want to reduce it to be a single stream. So we use reduce stream concat, which will then concatenate all the streams together into a single stream. And then we use collect to collect that into a list. And the reason to do this craziness is because we want to make sure that our program will run in parallel. And if we were to replace all this gobbledygook with flat map, we would get correct results, but they would not run in parallel because of the quirkiness of flat map. So an important idiom to understand, especially for assignment 3B, which is coming out soon. I think the last piece of the puzzle here is replacing reduce with sum. So there are situations where you can replace reduce with sum and arguably make the program easier to read. It can go either way on this one, but I'm just showing you the technique. So in this particular case, we're using sum. And the way it works is we take the character map, get the value set, turn that into a stream. We then use map to long. So now we're going to have a stream of primitives. And once we have a stream of primitive longs, we can then sum those results together. So this is one way to get the results, as opposed to having reduce. Now, it's really sort of 6 of one, half dozen of another, because we've got two operations, map to long followed by sum, whereas before we just had reduce, and we passed in the summation accumulator. So I don't really have a big preference. Sometimes it makes sense to do it this way. Sometimes it doesn't make sense to do it this way. Arguably, it's easier to look at this code and know it's summing. Maybe with reduce, you might have to look more carefully, and I guess there's opportunities for accidental complexity to pass the wrong values in at certain points. Okay, so that's the end of the second part of the reduce discussion.